Okay, so now we are recording. Okay, hi everyone. So, right, so we are doing this chapter 4, as you can see. So there are many sections in this chapter 4. So far we basically covered 4.1, 4.2, 4.3, 4.4. Not completely, but in some order. And so now it's time to look at some issues from 4.3 that need more attention, and then we will continue with 4.4 later. Okay, so one of the things that we have to do still from 4.3 is mixed higher partial derivatives. So 4.3 continued. Okay. So I can say the general heading for this would be mixed partial derivatives. Okay, so the idea is that once you take partial derivative with respect to x, there's nothing to stop you. You can take partial derivative again with respect to x or with respect to y, and you can just keep doing that. There's nothing to stop you at first order derivatives. Exactly like in functions from one variable calculus, where you could take higher order derivatives of functions. So you had f, f prime, f double prime, so on. Here also. But something interesting happens here because, so if we have a function like of two variables, then we can take, so let me just write it just as f. So this is f. Then we can do two things. We can just take f sub x, right? Or we can just do f sub y. Partial derivative with respect to x, partial derivative with respect to y, right? And then with partial derivative with respect to x, I can take another partial derivative, this time again with respect to x. So maybe just f sub xx. Here, let me not write that. Arrows, just simple lines. And then you can take partial derivative with respect to y. With this one also, you can do two things, partial derivative with respect to x of y, or partial derivative with respect to y again, right? So we can iterate this process again and again and again, right? So of course, this f sub xx really means partial with respect to x of partial of f with respect to x. I mean, that's a concise and very economical notation for second partial derivative with respect to x, right? So that's a good notation, because writing it like that, it will take forever, but this is just simple. And by the same token, f yx, by definition, is partial derivative with respect to y, and then partial derivative of partial derivative with respect to y of partial derivative of f with respect to x, right? And of course, similarly for this. But now you notice that we can continue this. So this thing grows like a tree, right? So it's just like leaves of a tree. I mean, not leaves, branches of a tree rather. Leaves are at the end. Like branches of a tree, they grow, right? So this is like a root. There are two branches here, and from this branch, again, sprouts two branch here, and then two branch here, and so on. So you can just continue, right? Like forever. Just goes on. So if you continue this, you get a nice kind of diagram of these branches that they grow like that, right? So now something. So let me give you an example before doing this. So here's an example. Let's look at some function f of x and y, for example. Let's take to be a function like exponential of minus x2 plus y2, for example. It's a function of two variables, right? So this is our f of x and y. So let's compute fxx, for example, and fxy and fyx. So the question is compute fxx, fxy, fyx, and that's it. I don't want you to compute fyy because of the symmetry of this problem. It's clear that if you compute fxx, then you can compute fyy. So let's compute fxx. Okay, so well, I mean, the solution would be we have to compute f sub x first, right? So this is f sub x. The partial derivative of this guy with respect to x is minus 2x, right? So derivative of that times exponential of minus x2 plus y2. Right? So that's, now let's take derivative of this with respect to x again. So if you take derivative of this with respect to x, that's d dx of this one. Right? Now, here, of course, we can use product rule or Leibniz's rule, right? Because it's a product of two functions. And for this matter, we are just considering y as a constant. So y is not changing, it's a constant. So this is like a product rule we can use. So that's equal to d dx of minus 2x is, of course, negative 2 times exponential of negative x2 plus y2. And then we have got negative 2x. Now, derivative of this guy with respect to x again, which we already calculated here. So this is again negative 2x exponential of negative x2 plus y2, right? So allow me to erase this. So now, overall, this factor, so we have to add these two things. This factor appears in both. So we can just factor this out. This is exponential of minus x2 plus y2. And then there is negative 2 here, and there is 4x squared, right? So there is negative 2 plus 4x. Right? So that's the result. That's f sub xx. Okay? Now, what is f sub yx? Okay, now we have to compute the derivative of this guy. So this is d dy of negative 2x exponential of negative x2 plus y2, right? It's just that one. Now, to compute this derivative, this is actually simpler because x is a constant now, so you can just forget it and we don't even have to use product rule. We can just take derivative of this with respect to y and product. So this is equal to negative 2x, in other words. And then derivative of this factor with respect to y is negative 2y. Exponential of negative x2 plus y2. Okay, so overall now what we got is that f sub xy what we've got is that f sub xy, yx rather. You just have to multiply this thing with 4xy exponential of minus x2 plus y2. Okay, so far we have solved two of these problems, fxx and fyx. Now we can do fy and then fxy, the other way around. So fy, well, this is completely symmetric, so I can just look at f sub x and then replace x by y. You get minus 2y. Or you can just compute it, that's not a problem. Minus 2y exponential of negative x2 plus y2. And fxy is equal to negative 2x, negative 2y exponential of negative x2 plus y2. Okay, so we are done. We calculated f sub xy, we calculated fyx, and we calculated fxx. Now, do you see anything interesting in this calculation? Do you see any interesting pattern or maybe feature here by any chance? Yeah, I will. Yeah.
That like the order didn't matter if we did x first or y first.
Exactly. You see, the order here, it doesn't matter. Here, fyx, we get 4xy, this factor, and fxy again is 4 yx or xy again, e to the minus n. So note that, and this is very important, note that here we have got fxy equal to fyx. I mean, it's quite strange that this should happen at all. You might think that, okay, this is a special feature of this problem, this function, and this is happening. But the fact of the matter is that, in general, under some very, very general conditions that this function f has to be satisfied, of course, this is true in general. This fact is true in general. So mixed partial derivatives, for mixed partial derivatives, order doesn't matter if f is a reasonably good function. That's what I will write down very soon. But we just noticed that this is true in this case at least, right? So the result that tells us such a thing is true is called Clairault's theorem in honor of a French mathematician, 18th century, Clairault. So let me now write it down, and then we will discuss. And then keep this kind of tree in mind. It grows. But now we are saying that actually these two branches meet each other at this point now, because fyx we are saying is equal to fxy, at least for reasonably good functions f. Right? So now I'm going to write down this theorem. So this theorem is on mixed partial derivatives. So this is also called Clairault's theorem. It just says that suppose f is defined in a neighborhood of a point P in R2 is such that the functions mixed partials derivative f sub xy and f sub yx are defined that's one condition. First of all, they should be defined. I mean, they should exist. Or sub xy exists. I mean, because there may be some confusion about what define means. Of course, we can define these things, but exists. And so, first of all, these guys individually exist. So it means that fy exists in that neighborhood, and fx of fy exists in that neighborhood. So this is a lot of conditions. And the same for this one. So first of all, exist and are continuous. In that neighborhood. Okay, then the theorem says that these guys are actually equal in that neighborhood. Right? Then fxy equal to fyx on D. So let me tell you what D is so that you know. The picture that we have of this neighborhood is a small neighborhood. So it's just in the vicinity of this point, because this is just about some small neighborhood around P. So this D is a disk, open disk. So D is the set of all points Q in R2, such that the distance between Q and P is less than epsilon for some epsilon, such that the distance between Q and P is less than epsilon. For some epsilon positive. By the way, this is called an open disk around this point P. That's an important concept. So this is an open disk around. So what you're saying is that your function is defined on this open disk, first of all, and then these mixed partials exist in that open disk, and they are continuous. Right? These conditions. Then we are guaranteed that mixed partials are equal. So this is for many functions that we are going to work, and in practice you see these conditions are kind of automatic. So you have to work kind of hard. There are examples, there are assignments that we will give you functions that you will see that these conditions, one of these conditions is not satisfied, and as a result, these mixed partials are not equal. But those are pathological functions. They are not kind of norms for us. They are pathologies, right? They are exceptional cases. They are not norms. Okay, so that's the result. Now, this is for functions of two variables, but there is nothing to stop us for functions of two variables. We can look at functions of three variables, first of all. And then we can continue this in higher order. So as a result, some interesting patterns will emerge, as you see. So let me just make it like make a statement like this. Similarly, for a function of 3 variables, under similar conditions, I won't write this again because you know how to formulate it, the similar conditions here. Under similar conditions, we have, okay, we can actually now claim that, yes, this mixed partials fxy equal to fyx. fxz is equal to fzx, and fyz equal to fzy. You see, we have more possibilities here now. You can take partial with respect to x, or with respect to y, or with respect to z, and then you can take with respect to the other values. And what this result says is that, yes, you can switch the order of derivatives between x and z, between y and z, and between x and y. This is the reasonable statement for 3 variable functions, right? So that's the 3 variable case. But still, you don't have to stop there. You can just use this and then apply this to higher order mixed partial derivatives as well. So that's, you can continue now without paying any bigger price now. The result is true now. Okay, similarly, of course, if higher derivatives, I would say higher mixed derivatives, exist and are continuous, again, by under those conditions, on that open disk around this point P, then we can say, for example, take 3 things, x, y, z. You see, you're taking partial with respect to z, then partial with respect to x, now partial with respect to y, right? Or you can do it like this. You can just say, well, you want to start partial with respect to x to start with, partial with respect to z, for example, and then y. Any order that you change these variables x, y, z, will give you the same result. So, and how many possibilities do you have in this case?
6.
Exactly, thank you. Yes, 6 possibilities, because it's a number of permutations of 3 letters, right? Number of permutations of 3 letters x, y, z. There are 6 possibilities, and they all give you the same result. So equal to f, say y, zx, etc. So 6 cases. Right? So we have 6 cases. Of course, you don't have to take partials with respect to different variables. You can repeat the same variable. For example, you can do fxx, y. And then you can say, well, you can switch this to, you can just say this is fx, yx, right? And this is equal to fy, xx, right? So this can go, you can switch this to, you can switch this to, and then, yeah, okay, so You can also play the same game by bringing Z into the game and all this. So any sort of combinations with these and higher variables works under these suitable conditions with higher derivatives. Mixed partial derivatives should exist and they should be continuous. And so this is sort of reasonably good or well-behaved functions are like that. There are functions, and we'll see many examples of those, well, not many, but some examples, that they don't satisfy these conditions. Okay, so this result is very, very interesting because it reflects some fact about mixed partials, which becomes extremely useful in calculations and in applications of mixed partial derivatives. Okay, any questions? Okay, looks like there are no questions now. Let me now go and consider and define some other concepts which are important. So this concept, for example, is the idea of partial differential equations. So there are examples and there are problems about this in your text. So. Okay, so this is a great application of idea of mixed derivatives where we form differential equations for an unknown function, but this function is not a function of one variable, it's a function of two variables, right? And these are called partial differential equations. The best thing I can do is just to start by examples, and you don't have to know the general definition. So here's an example. So this is called the Laplace equation. So what is this absolutely fundamental Laplace equation? This is the equation d2u dx2 plus d2u d by 2 equal to 0. Now, one thing that I'm using here that I did not introduce this notation up here, so let me introduce the relevant notation here, and then you'll see that what this means. I'm sure you are already seen this in other courses, but let me just introduce here. Where, I would say, comma, where, that is, d2u dx2 is, by definition, what? The second partial derivative, right? d2u dx2 really means d2u, I mean, so let me write it like this, means u xx. So this is like d2u dx dx. Okay, so the best and most economical notation is, of course, this one. This is what is used here. I'm using here just to introduce the concept. But you can, so Laplace equation, you can write it it can also be written as uxx plus uyy equal to 0. Okay, so this is the celebrated, the world famous equation, partial differential equations. One of the champions of partial differential equations is Laplace equation. It's this equation, or equivalently this equation. Now, a function that satisfies this equation, do you know what's it called by any chance? I don't expect you to know it. I mean, maybe in your electrodynamics or electromagnetism courses, EM courses, you have seen the definition. These are called harmonic functions, right? So this U, a solution, U is called a harmonic function. That's a very important class of functions, harmonic function. In other words, a harmonic function is a function that's defined on some open set or somewhere such that this condition satisfies the Laplace equation. In other words, the solution of the Laplace equation. Okay. Of course, you don't have to stop at dimension 2. You can go to dimension 3, dimension 4, and all higher dimensions as well. So let me just say, so go to higher dimensions. So this is in 3D. Your equation is uxx plus uyy plus uzz equal to 0. So this is Laplace equation. Okay, so let's take a function like this. So here's an example. Let u of x, y, z be equal to -1 over r, which is -1 over square root of x2 plus y2 plus z2, right? This. Okay, so this function, can you tell me what's the domain of this function? Obviously, this function defined everywhere except at the origin, right? So the domain is everywhere except at the origin. It's not defined at the origin, right? So so origin is excluded. Okay, now let's compute ux. What is ux? Just not to make mistakes, I'm going to see this as -x2 plus y2 plus z2 to the power -12, right? And let's take partial derivatives with respect to x. Then this is equal to half 2x times x2 plus y2 plus z2 to the power -3 over 2, right? Good. That makes sense, right? Now let's take uxx, another partial again. Of course, this is now with respect to x is x2 plus y2. So we have to use product rule, right? Here. So this is x2, y2, z2 to the power -3 over 2. This is, I took derivative with respect to x. This 2 and this 2 cancel, by the way, so don't look at them. They'll cancel. So this is x2, y, and then this is -3 over 2 times x is there times 2x, right? Times x2 plus y2 plus z2 to the power negative what? 5 over 2, -3 over 2, -1, no, -1, which makes it -5 over 2. Cool. So now this is equal to, okay, so I've got x2 plus y2 plus z2 I'm going to write everything in terms of R actually. That's easy. Well, it doesn't matter. Let me just write. Negative 3 over 2. And now there is a simplification here. So this is negative 3x squared. Right? Negative 3x squared. Then I've got x2 plus y2 plus z2. The power negative 5 over 2. Okay. So what? Now what can we say about this? Okay, so let's, now I'm going to say, let's compute uyy and uzz, right? So, but to compute uyy, there is a shortcut. You don't have to, suffer computing uyy again. You can just tell me what uyy is from what uxx is, right? Why? Because of symmetry, right? Because x, y, z in this function play a completely symmetric role. I mean, the role that's played by x is like the role played by y and z. They're completely symmetric. So it means that uyy, I just have to look at this and replace x by y. That's it. So this is equal to x2 plus y2 plus z2 to the power negative 3 over 2, negative 3y2 to the power x2 plus y2 plus z2 to the power negative 5 over 2. And similarly, uzz, same, is x2 plus y2 plus z2 to the power negative 3 over 2, negative 3z2, finally, times x2 plus y2 plus z2 to the power negative 5 over 2. Now, let us add these three factors. Now you can see where I'm heading, right? So let's add uxx, uyy, uzz. So you get that uxx plus uyy plus uzz is equal to, if you add these things, this factor is common between them. So you get 3 times x2 plus y2 plus z2 to the power negative 3 over 2. Negative. Then there is this factor 3, x2 plus y2 plus z2. You just factorize those terms. Negative 3 times x2 plus y2 plus z2. And then there is a common factor x2 plus y2 plus z2 to the power minus 5 over 2 times x2 plus y2 plus z2 to the power negative 5 over 2. Okay, so this is uxx, uyy, uzz added together, we get this. Now, can you tell me what is the result here?
0.
It is absolutely correct, exactly, thank you. It's 0. Why? Because you just see that, you see this term, there is 3 and 3 here. This term drops a factor of this power minus 5 over 2 from minus 5 over 2 to minus 3 over 2. Because this cancels one factor here and then becomes minus 3 over 2. And there is minus 3 over 2 here and 3 and 3. So this is equal to 3 times x2 plus y2 plus z2 to the power negative 3 over 2. And then we have got negative 3 x2 plus y2 plus z2 to the power negative over 2. And this is equal to 0. And this is an amazing result. I mean, So what did we discover? We discovered that the function minus 1 over r is a harmonic function. The function minus 1 over r is a harmonic function. So what is the importance of this function? Maybe you have seen it in other courses. What this function is telling us? It's a function that, if you think about it in clear space like x, y, z, so it's a function whose value at each point is inversely proportional to the distance. I mean, this minus 1 sign, don't mind right now. It doesn't matter, because if you multiply it, if you just take 1 instead of minus 1, this would be the same, would be a solution again. It doesn't matter. For now, it doesn't matter. Later on, it will matter. But for now, it doesn't matter. But just look at the behavior of this function. This function is constant on these spheres of radius r, right? It's a constant. On each sphere of radius r, at all these points, the function is constant, and its value is 1 over or minus 1 over the distance. So as you go out to infinity, this function diminishes, right, with the ratio of 1 over r. On these spheres is constant, and it gradually approaches 0 at infinity with this speed. And then as you get closer and closer to the singularity, to 0, it gets bigger and bigger, but with this rate, 1 over r. This function is the potential function for gravitational force and for electrostatic force of a charge that's located at that origin, right? So now, this is not part of what I expect you to know, but I'm sure many of you have seen this in your physics courses. This is a potential function. So we'll see that later on, but I wanted to do the calculation here. For a force field, for a force field, I would say gravitational force field, for example. Gravitational force field of a mass at the origin. If you have a mass, it doesn't matter how big the mass is. Well, just if you have a mass of m, maybe you have to put a factor of m here, but that doesn't matter for our discussion. Let's assume there's a mass, unit mass, and this mass, Newtonian potential, right? It has some attractive force, but the force drops as what, or increases as what? 1 over r squared, right? But the potential of the force changes as 1 over r. There's a difference between the two, right? So this, as you go to infinity, drops like 1 over r, but Newtonian potential drops like 1 over r squared. Well, because this is the potential, it's not the force itself. We'll discuss that later on. I mean, in fact, it becomes very, very important, but I want you to keep this in mind, that the function 1 over r is not just any kind of garden variety function that you have to respect that function. That's a very, very important function. It's like exponential function, log function, this sort of functions that are important. 1 over r is also very, very important function. It's a lovely function. It has many properties. I just showed one property, which is the solution of this Laplace equation. And from that, a lot of other things follows, but anyhow. Okay, so we just checked that this is the thing, this is the solution. So there are two other partial differential equations that we will discuss. One is the wave equation, and the other one is the heat equation. Okay, so these equations are very important in applications, and I just write the wave equation, and then we will discuss wave equation next time. Okay. Any questions?
Yeah, I have one. So are all harmonic functions symmetric necessarily?
Oh, not at all. No, that's a wonderful question. Thanks for asking. No, not at all. There could be, now you might ask me to give you an example perhaps, right?
Sure.
Okay, I'll be hard pressed to give an example, but I'll do my best. Let's look at.
All right, thank you.
What's that?
Thank you.
Sure. Yeah, no, that's a wonderful question. Thank you for asking. So, yeah, the question is it true that all harmonic functions are symmetric? So let me give you an example. Let u of x, y, z equal to x2 minus y2. So what is uxx? Is 2, right? Uyy is -2. Uzz is equal to 0. So this is a solution then. Equal to 0. And so, yeah, so this is a harmonic function. U equal to x2 minus y2 is harmonic. In a similar fashion, you can show that u equal to x2 minus z2, u equal to y2 minus z2 are harmonic as well. So these are very simple examples of functions which are not symmetric. I understand by symmetry you means they have a spherical symmetry, right?
Yeah.
So they would be like just depend on distance. So you are saying this would be just a function of this distance r. No, but I know why maybe you asked this question. That's an interesting question, because you guess that somehow perhaps we can construct all harmonic functions from maybe this 1 over r function, right? Somehow this is kind of the mother of all harmonic functions, 1 over r. And in fact, this is true, but it needs some explanation. But that still doesn't imply that all harmonic functions are symmetric. Although the mother of all harmonic functions is symmetric. Its kids are not symmetric, sorry.
All right, thank you.
Sure. Anyhow, so yeah, that was good. So, okay, so I think I better leave the wave equation, the venerable wave equation, the magnificent wave equation, and heat equation to the next lecture. All these three equations are wonderful equations. They have many applications. I mean, they have helped us building a lot of things around us, just solving these equations. Any other comments or questions? So again, sorry about the chat. So I'm going to ask and fix the chat next time for sure, because this is done by the administration. So we have to figure out how to do it. But for now, we are good. So I just stop.